Hey, welcome back to my Introduction to Mathematical Proofs playlist. Today we'll be talking about a technique called dovetailing. So last video we introduced cardinality as a concept, then we looked at the cardinality of the evens and found that it's the same as the cardinality of the naturals, and we call this infinite cardinality the countable. We sent in PHP to an interesting use case, and then we ended by looking at the cardinality of the integers, which is also countable, which is the same as the cardinality of the naturals. So there's going to be two main sets of focus today, and we're going to be looking at the cardinality, namely n cross n, or n Cartesian product n, and the rationals. Before we start off, let's just prove this kind of useful condition. If A is a subset of B, then the cardinality of A is less than or equal to the cardinality of B. This is something that you should be able to do with a little bit of time. We just noticed that since A is a subset of B, that means every x in A is also in B, so we should be able to use the map f of x is just equal to x, and this should be well defined, as in the function should exist and it should be defined for every value. This function must clearly be injective. And you understand why? Remember, by definition, A subset equal to B means that if x is in A, then x has to be in B. So clearly f of x is equal to x has to be injective. And we'll never have that the cardinality of A is greater than B. So we must have that the cardinality of A is less than or equal to B. Let's warm up by looking at some set operations before we go to the Cartesian product. Let's first look at union. What can we say about the cardinality of A union B when we know about the cardinality of A and cardinality of B? By definition, we know that A union B is everything that's in A and everything that's in B. Or you could use everything in A or in B. That's another way we could think about it. So we must have that A is a subset of A union B, and because of our proof that we did last time, the cardinality of A is less than or equal to the cardinality of A union B. And the same thing will also be true for B, so the cardinality of B will be less than or equal to the cardinality of A union B. And you can probably think of some finite set examples, but we'll do an infinite case. If E is all the natural even numbers and O is all the natural odd numbers, well, we proved last time that the cardinality of the even numbers is countable. You can also prove that the odd numbers is countable, and that's the same as the natural, so it's less than or equal to. Even though the even numbers union the odd numbers is the naturals, all of them can have the same cardinality, which is really weird to think about. But this is just kind of what you get when you're messing with infinity. Now let's look at intersections. And you'll notice that our conclusions are reversed, because instead of A being a subset of A union B, we're going to have A intersection B as a subset of A, and A intersection B is a subset of B. So we must have that the cardinality of A intersection B is less than or equal to both the cardinality of A and the cardinality of B. You should be able to think of some examples. One interesting thing here is if A is a countable set and B is a finite set, then A intersection B must have finite cardinality, because once again, both of these conditions must be true. Now, difference and complement. Difference is pretty similar to the case for intersection, because we have that the difference of something is a subset of the original set. So if we have A remove B, that's a subset of A, so the cardinality of A remove B will be less than or equal to the cardinality of A. Now, regarding complement, it becomes a little tougher because it depends on our universal set and the set A. We must have the cardinality of A complement is less than or equal to cardinality of U. But, anything else is kind of like hard to think about, so we're not going to worry about this. Now, this is the main boss right here, Cartesian product. In finite sets, well, we must have that the cardinality of A Cartesian product B is the cardinality of A times the cardinality of B. Think about this. If you have a set with 3 elements and a set with 3 elements and Cartesian product them, the cardinality becomes 9. There's 9 elements in A cross B. But the problem here is with countable sets, how do we multiply countable cardinality? Because remember, countable isn't like really a number, right? The particular set we're going to be looking at is n cross n. What's the cardinality of this set? The following grid describes n cross n, I think, pretty accurately. So just take a look at it. If you go to the right, the first component increases. If you go down, the right component increases. And maybe you can see the issue. Like, it goes to infinity in all directions. It goes to infinity to the right, down, like diagonally down, right? Like, how would we prove anything about its cardinality? Like, is there an algorithm to count up every single pair? Can we come up with such an algorithm? If so, then we should be able to say that, hey, this is a countable set. If not, then what happens then? And remember what we had to do with the integers? It went off in 2 directions, but what we did is make it go off in 1 direction. We created a sequence and the ... goes off in 1 direction. How do we do this here? Remember the problem we have with the integers? We can't just go right and then eventually turn around, because we'll never end. For example, if we were to consider the sequence 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, and keep going that way, well, it wouldn't get anything else below that whole entire first row. So we need to find a way to put this all in like a one-dimensional sequence. And when I learned this technique, we call it diagonalization, but that's actually like not the correct name. There's actually a name to describe it. It's called dovetailing. And to explain what it is, we're going to pull out the animation budget. So here we have our original set. Just for now, we're going to be looking at a 5 by 5 grid. Of course, I can't show infinity to infinity, so we're going to assume that this goes to infinity towards the right and below. Well, we're going to start on the top left, and we're going to make it 1, 1. And we're just going to put it on the right, so you can see that it becomes a sequence. Then we're going to go down, then back to the top right, and you're like, okay, and then how does this help? What's different here? Then we go to 3, 1, then 2, 2, and then we're going to go to 1, 3. And you're like, I don't understand what's happening. Well, we're doing each diagonal. So we're covering each diagonal first. So the first diagonal is 1, 1. The second diagonal is 1, 2, 2, 1. The third diagonal is 3, 1, 2, 2, 1, 3. The next diagonal is 1, 4, 2, 3, 3, 2, 4, 1. And if you do every single diagonal, you'll eventually hit every single number. If you think about it, it's like sending a line from the top left all the way down to the bottom right, and it just keeps growing and growing and growing. There's a few interesting consequences. In this case, each diagonal is actually a sum of a number. So the first diagonal is a sum of 2. The second diagonal is a sum of 3. The third diagonal is a sum of 4. And you'll notice we stopped the animation at this point right here, because if we were to have an infinite grid, where we would go next in the process is 1, 6. But of course 1, 6 doesn't exist, so we just stopped the animation right here, because once again we're thinking about this in infinite dimensions. Think of what's happening. We're going diagonal, diagonal, diagonal. That's the main idea here. So the idea is this: dovetailing allows us to take a whole entire grid and put them into a single sequence by counting or iterating through every single diagonal. Of course, diagonal is like loosely defined. There's really no other way to describe it. Intuitively, it makes sense, oh, the diagonal of the grid, but, how would you rigorously define this is something that we'll have to deal with. And yes, this actually works in higher dimensions as well. You can do this for a 3D grid, a 4D grid, and so on and so forth. So now let's start by proving the claim that n cross n has countable cardinality. What we're going to do is we're going to arrange every element in n cross n in the following way. The first thing we're going to do is we're going to group elements together. So let's say that AB is an element in n cross n. We're going to group them into categories by a plus b. For example, if we have 3, 2, this is going to be grouped into category 5 alongside 4, 1. And we're going to denote this as G5 since the sum is 5. So if instead it were to sum to 7, we would call that G7, for example. If it were to sum to 9, like 8, 1, or 7, 2, or 4, 5, that would be G9. Then what we're going to do is we're going to iterate through each group starting at group 2 or G2. Because 1 plus 1 is equal to 2, and 1's the smallest natural number, we can't have G1. Now, we're going to notice that each group has a finite number of elements, because cardinality of Gn is less than or equal to n. But the reason why is because the ways that you can arrange a plus b is at most n. So we'll be able to reach every group after enough time. Now, the sequence in all of its glory will be G2, G3, G4, G5, but then when we expand that out, it'll be 1, 1, then 1, 2, 2, 1, 3, 1, 2, 2, 1, 3, 1, 4, 2, 3, 3, 2, 4, 1, and so on and so forth. So this is what we mean by iterating through every single group. Now, this map is actually bijective. Well, let's look at surjectivity first. We know that if a comma b is an element of n cross n, we know that that element will be in the group a plus b. So eventually it will get mapped to, because we're going to count every single group. And for injectivity, we notice that any one element can only be in one group, since a plus b is always a plus b, and we don't allow duplicate elements by definition. So we must have that each element is only mapped to once. That is, an element will only appear once, so there's no way that we will fail injectivity. So if x1 is not equal to x2, there is no case that f of x1 will be equal to f of x2. That is not possible, because there are no duplicates. And this just shows that the mapping or function is bijective. One quick thing to note here is that we never really explicitly defined what f of x is, so I'll just give you a few examples. Here, f of 1 will go to 1, 1, f of 2 will go to 1, 2, f of 3 will go to 2, 1, f of 4 will go to 3, 1, f of 5 will go to 2, 2, f of 6 will go to 1, 3, f of 7 will go to 1, 4, and so on and so forth. If you think of the natural numbers as being right underneath our sequence, you should be able to see why putting it into a sequence is actually sufficient. Because if you can put it into a sequence, that means that we can map the natural numbers just by sending 1 to the first thing in the sequence, and 2 to the second thing in the sequence, and 3 to the third thing in the sequence, and 4 to the fourth thing in the sequence, and so on and so forth. This is why showing that we can arrange things in a sequence, that's sufficient. What's really annoying is we didn't explicitly define f. And, I know last video we said that, hey, it's better to define f, but it's actually really hard to come up with f in a smart way. There's no really good function to derive it. So we had to argue it by other means. And once again, it all comes down to rigor. How rigorous are you with your proof? If you can define f, then we should. That's the main idea. But in cases where we can't, we're going to have to argue it like we did in the previous proof. Make sure you understand how the previous proof worked. The idea is we took a two-dimensional grid and used a technique called dovetailing to count every single diagonal starting from the top left, and it'll keep going down to the bottom right, but it goes to infinity, so there's never actually really a bottom right. So it'll keep crisscrossing back and forth, and then we can arrange this whole entire thing as a sequence. And then that's bijective, because one, it'll reach every single element because we count each diagonal, and in every element must be in a diagonal. And it's injective because we don't allow duplicate elements. Once again, think of the big idea, make sure that makes sense. But unfortunately, there's a few limits to dovetailing. So this won't work for infinite dimensions. So if you have an infinite or countably many Cartesian products, well, that sucks. You can't figure out how to do it. It won't work. And the second thing is we need to figure out how to arrange our elements in a grid or into these diagonals or groups or whatever. So that's kind of the hard part. And what's really interesting here is that dovetailing is like a really whack technique. Like it doesn't come up often, right? But I think we learn it because it's cool, right? It's really fun and it's pretty thought-provoking. I think it's one of the more interesting things that happens in the first half. But it probably has to do with thinking outside the box. Remember, we're learning math to figure out problem solving, learn tools and whatever. The idea is we're building the meta mathematical skills. We're building the meta skills to be able to think. That's why dovetailing is kind of unique in that aspect, because it's a technique that you won't use, but it helps with that problem solving or thinking outside the box or being able to understand different ideas that people come up with. Once again, even if you never use it, just knowing how it works can never ever hurt you. Okay, we'll do one more. What's the cardinality of the rationals? And the rationals are actually really, really special. Between any two elements, we can always find another element. So in this case, we did 21 over 5 and 22 over 5. We found the element 43 over 10. So this property is called density, or we say that Q is dense. So it's really interesting because, okay, if it's dense, we need a smart way to count up every single number in the rationals. We can't just do it how we did the naturals and the integers. We need to figure out a way to order it. Remember how in the naturals are like, okay, 0, what's the next biggest element? Well, it has to be 1. In Q, there's no such thing as a next biggest element, because if you were to claim that, hey, there is a next biggest element, well, no, you can't. There's another one in between. So it's really hard to formally come up with a nice ordering. You can't just start from negative infinity and go to infinity and just count that way. That's not possible. So we're going to come up with a really clever way to figure out how do we count every element in the rationals. There's two ways that we can think about this. This is the first way we can think about it. The rationals is just like the integers, but instead of just going left and right, it also goes down, just like this. But then the issue is we have to remove duplicates because Q has to be in lowest forms. So then the grid will look like this. There still will be infinitely many elements, but it goes in every single direction. And if we were to go further right or further left, like include one more column, we'd have to remove stuff like 3 over 6, since that's like 1 over 2, or negative 3 over 3, because that's just negative 1. And the issue here, compared to the n cross n case, is that this goes in 3 directions, left, right, and down. Can we turn this into a grid that only goes in 2 directions? Is there a way that we can kind of get rid of one of the directions entirely? And we can. Just act like the negatives don't exist, and every time we see a positive value, we're just going to add the negative version in there for free. And now, here's another way that we can count Q. We use this thing called total value. For example, 4 over 3 has a total value of 7, or 1 over 2 has a total value of 3. All we're doing is adding the numerator and denominator. And this seems awfully familiar to the n cross n case, but there's a few key differences. Let's see if you can catch them. So we're going to be showing that the cardinality of Q is countable. We'll arrange Q into a sequence as follows. First, we're going to put every element in the group dependent on the absolute value of the sum. So A over B will get put into the group of absolute value of A plus absolute value of B. It's not nice to deal with negatives. You know, it's really annoying because like if you deal with a negative 3 over 2, that goes to like negative 1. Negative groups is really annoying because you can have like infinitely many. We just don't worry about that. Then we'll count or iterate through every single group as follows: G1, G2, G3, G4. You might be like, okay, this is fine, but we're actually going to come up with an issue. We're going to get duplicates. So what we're going to do is when we create an arbitrary group, let's say Gn, we're not going to include elements that aren't in lowest forms. For example, 2 over 2 is just not an element of G4. This means that we can find injectivity. And once again, since each group is finite, it's less than 2n, every single group will be reached by our algorithm. So there's no, will it like forever be stuck on one group? That doesn't happen. So now what we're going to do is we're going to expand our sequence, G1, G2, G3, G4, by listing out every element in each group. So in G1, we just have 0, that's fine. In G2, we have 1 and negative 1. In G3, we have a half, 2, negative half, negative 2. In G4, we have 3, a third, negative 3, and negative a third. Notice we don't have 2 over 2, because once again, things in lowest form are not allowed. Then we'll show that the naturals map to this sequence bijectively. Regarding surjectivity, we know that if A over B is a rational number, then it'll be in the group of absolute value of A plus the absolute value of B, so it must get mapped to. 2. So every single rational is in a group. And since we go through every single rational, this is surjective. And regarding injectivity, we know that we don't allow any duplicates. So we must have that each element only appears once. And because it's only mapped to once, there's no way that if we have two different x values, then they would have the same output. So the mapping and function is bijective. We have shown that the rationals has countable cardinality. What this means that we can find an algorithm that counts through every single element. It finds every single element in the rationals. And there's two things we can do from here. We can either go on to countable Cartesian products, but this is not something we'll deal with. This is something that you'll be able to prove later. The cardinality of the reals. This is what we'll tackle next time. Until then, bye.